Going on, North Gwinnett? This is Mr. Dab here. I'm going to give you the secret to being awesome at physics. This right here is going to be a premise. You can understand some of these concepts, and we'll keep going over them. But this is going to be hopefully really helpful for you guys. Okay, because I just remember not too long ago when I had confusion about some of this stuff. So I'm going to try to hit this so it makes a little bit more sense to you guys. Okay, so the first thing I'm going to start with is variables. First thing you guys got to know about variables is that really we have our tried and true variables that we use in physics that you'll see in the equations on your formula sheet. But really, guys, at the end of the day, it really doesn't matter what you use as long as you know what it means, right? So you could have written out initial velocity, the whole entire word for a variable if you want, right? And now it's going to be painstakingly long to do that every time. But as long as you know that that phrase means the initial speed with the direction, right? Obviously, we can also use this guy here, which is V naught, that little zero. Whenever you see the zero in physics, that usually means like beginning or like initial, right? So I'm totally okay with, if you feel more comfortable, some students like to say V sub I, meaning V initial, okay? Now, the thing I'll say about these variables is the first few times y'all see something like this and you see an equation with V sub I in it, you're going to freak out and be like, what does the I mean? What do I plug in for I? It means nothing other than it's just telling us what type of velocity, right? Because we have different types. We have final, we have average, and we have initial, right? And so V sub I is just saying that it's the initial velocity, right? It's still just a velocity, nothing special, but it's just denoting that it's an initial velocity, right? So the V naught here on the left with the zero or the VI both mean the same thing as that word up there, right? As this phrase here, which is initial velocity, right? And so when you see an equation, like we'll see here in a second, V final is equal to V initial plus acceleration times time. The F and the zero, you're not going to have to do anything with, right? It's just letting you know that one of them is going to be the velocity in the beginning and one's the velocity at the end. They're both meters per second, so don't let that confuse you or freak you out when you see some of these extra symbols in the equation. It's just a denotion of what it is, right? So technically, you could write anything you want. You could write out up here, right? You could say V initial. Now, once again, it's going to take you forever, and I wouldn't recommend this. But if that's what you need to do in order to always remember that that's the initial, that's completely fine. And so then in my extreme case, obviously we'll use this equation down here, and I'll say, I could say, well, I'm going to use smiley face, right? So I'll use frowny face for final equals smiley face, which is initial, plus acceleration. We'll make acceleration the scared face, and then we'll say time is times, what kind of face could I do for this? We'll do like the puzzled or freaked out face, whatever you want to call that, right? So technically, obviously I would never recommend you guys do this, but I just want you guys to know that as long as I know that my smiley face is initial velocity, my scared face is acceleration, frowny face is final, and my weird face is the time, I could technically still use this equation, right? So I just wanted you guys to not be freaked out about the different variable denotions. Whenever you see that extra letter, it's just telling you what version of that variable it is. You don't have to actually plug anything in. There's no weird mathing you have to do, right? It's still just a variable. It's just saying, hey, this is initial, right? So then we move to our equations here, okay? The thing you guys want to be able to do is if I say on this first equation here, if I say, hey, I want to isolate t, can you do that without any numbers? Right? And so what does that look like? Well, remember in math, right now I've got a plus initial velocity on the side, then I have acceleration times time. Well, to get the initial velocity over to the other side, I'm just going to subtract, right? Subtract both sides by initial velocity. So then I end up with final velocity minus initial velocity is equal to AT, right? Well, now I want to isolate t by itself. So A needs to go on the other side, which means I will divide both sides by a. Since we're multiplied on the right, I'm going to divide both sides by a, right? So obviously when I divide by a here, cancels, and then I'm going to divide by a over here. And so now I have successfully isolated t, and I know that it is final velocity minus initial velocity over acceleration, right? And that should make a little bit of sense to you guys, right? But we want to be able to isolate these things, right? And so then a trickier one, let's say we want to isolate this delta x. And delta x is another one of those, don't get freaked out. This is the same thing. Some people will write the letter D for displacement, but delta x is just change in position. Whenever you see that triangle looking thing it always means changing, right? Once again, not having to do anything with the triangle, just showing us that this is a change, right? That there's a change. It's not just one value, it's the difference between two values, right? So whenever you see that delta x, we use it a lot in physics, or delta v, delta, there's all sorts of deltas. Just know delta t, right, is all just change in. It's a change from start to finish. So let's say now we want to isolate that delta x, right? And so I'm going to say, well, the first thing I would do is subtract over the initial squared, right? So now I have v final squared minus v initial squared equals 2a delta x. And so here I can do it in one step. I can say, well, I'm going to divide by 2a, right? So vf squared minus v initial squared over 2a will give me delta x. And so you can see we just got to practice that moving variables around, manipulating those variables to isolate things. And so your question might be like, well, why would I do this? Like, why not just plug in numbers and do it the way I'm used to? And I will show you an answer to that here in 1 second after you cover this real quick scalar v vector, right? We'll talk about this more in class, but the scalar v vector is just, I want you to think about vector has distance covered, so 5 meters per second, right? That's a speed right now, which is a scalar, right? Because I have no direction. So this is scalar and it's speed, right? And we use speed and velocity interchangeably, but in physics, technically, there is a difference, right? A velocity would be 5 meters per second south, right? Or negative 5 meters per second, technically because it has a sign, would be backwards, right? And so as long as we can denote a direction from the unit or from the quantity, then that means it's a vector, right? So you'll see vectors a lot in physics. Forces are vectors, displacement is a vector, velocity is a vector, momentum is a vector, but things like speed is a scalar because it has no direction. Temperature would be a scalar because it has no direction. And so you can kind of start to envision pretty easily what's the difference between each one, right? So up here, when I talk about substitution, right? Substitution, and this is the tension equation, which we won't see for a few, for a month or two. But what I wanted you to know is that a lot of the times once you get to higher level physics, you might have two equations for like one portion of tension. Like, so this first equation up top is representing the tension in one string, and the equation on the bottom is representing tension in the second string. Well, a lot of the times in our tension problems, tension 1 is equal to tension 2. And so a way to solve this equation would be to set these equal to one another, right? So it would end up being m1g. So we'd have m1g minus m1a equals m2g minus m2a. And generally it would actually be plus here. And so then I could say, well, hey, isolate a, right? If they're both the same, can you isolate a? If they're different, what would we do? Or do we have enough information to solve? Questions like that, right? Generally, they will be the same, and so you would be solving for just A, and so this would be a more complex isolation problem, which we will talk about later. But mainly, I just wanted to show you guys that you can plug in for one another if the values are equal, right? If I say that force 1 is equal to force 2, and then you have an equation for force 1 and force 2, then you can set those equations equal to one another and solve, right? That's a big trick for once we get into more complicated things, right? And so now I'll go ahead and show you why it can be helpful to not use numbers. So we're going to look at what's an energy equation. And once again, you're not supposed to know what these mean. I'm just trying to show you guys why the math helps us out here, right? So here in this energy equation, this is actually when we're going to prove why mass doesn't matter when it comes to this like free fall or these free fall situations, right? Because here, if I was to say, hey, isolate H for me, right? Well, to isolate H, you would divide this other side by mg, right? So it would end up being mv squared over mg equals, or let's leave the 1/2, equals H. But since they both have m on top and bottom, we can cancel, right? So then that just leaves us with v squared over 2g is equal to H. And so what if the problem didn't give us mass, right? And it was like asking us to solve for H. Well, if you didn't do it this way, then you'd think you don't have enough information because you'd be looking for something to plug in for m and you wouldn't have it, right? Because it would cancel out. And I know this is a lot of information. That's why I wanted to make a video so y'all could watch it. But I just want y'all to start being exposed to some of these reasons why we do these things, so it'll make a little bit more sense once we actually dive in, right? So that is why, right here is one of the main reasons why we like to try to stay in variables as long as possible, because a lot of the times we can cancel something out, or, make it easier for us to solve for something. And then the last thing I'll cover today, just real briefly, is when we're talking about vectors, I want you guys to understand that in physics, there's this, which if this was your only line, right, this is one dimension, right? You can only go forwards or backwards. And generally, not always, but generally, would say negative is backwards and positive is forwards, right? So this would be what's called one-dimensional problem, right? Oop, didn't mean to do that. Okay, so in a one-dimensional problem, negative is backwards and positive is forwards, right? And generally, your vectors in that situation have to be one direction, right? And so if I'm adding these vectors together, we'd use tip to tail, which we'll talk more about, but this way is just going to be left to right. Now, occasionally you might see one-dimensional vectors being added, two separate one-dimensional vectors being added. So say it's like a vector like this plus a vector like this. Well, that's one dimension up and down, one dimension left to right, and together will equal up, down, left, right, which is what you guys are mostly used to, 360 degrees, right? And so here, whenever we add these vectors in this situation, we would end up having something like this, right? And so once again, I don't expect you guys to master this. I just kind of wanted to give us an initial exposure so that we know, about these vectors and how generally we're going to be adding vectors. In the beginning, we'll be adding one-dimensional vectors to create this two-dimensional vector. But once we get a little bit further along, then we're going to start adding these vectors. Like we could see 100 meters per second at 60 degrees like this, plus like 50 meters per second at 40 degrees, right? And the most important thing for you guys to remember is your trig here, right? This is where all this stuff is going to come from. It's a right triangle, okay? And so we want to create an x and a y piece so that we can, in physics, we like to keep all the x's and y's separate. We like to do everything with x's first, everything with the y's first, and then see what we can figure out with both of them, right? And so here, I want you to think about, I'm not going to tell y'all now, but I want y'all to think about, if I wanted to find y and x, what could I use from SOHCAHTOA that would give me the y and x components if we knew that 100 is our hypotenuse and 60 degrees is our angle. So I want you guys to think about that, and we'll talk about more breaking into components. Once again, I know this is a lot of information. I'm going to kind of keep hitting this with you guys, but I just wanted y'all to start to see, mainly the big thing today is to understand variables, symbols. If you have a subscript, it's not the end of the world. It's not something special. It's just saying, hey, this is initial velocity, right? You're still just treating it as one variable, but it's just saying, hey, it's initial velocity. And then also we want to practice isolating variables without using numbers, because that makes life so much easier when we get to more complicated things. And then just knowing that you have the ability to substitute like things, right? If the two things are equal and you have two equations for that thing, then you can set them equal and maybe solve some stuff that way. And then lastly, just understanding that, we could have just an x direction, we could have x and y, and then in physics C or higher level physics, you'd have x, y, and z for three-dimensional motion, right? Which we won't cover in AP Physics or CP Physics, but I just want you guys to know that technically, yeah, we could still do the same stuff for 3 dimensions, right? But we do stop at 2. Anyways, I hope this is helpful for you guys. We will continue to work on this. This is just kind of like a brief overview, but I'll look forward to seeing you guys soon, and we will get this done. Until next time.